Okay, good day. We are solving a problem, a welded problem connection from May 2015 board exam. So the problem states that the vertical member of a truss is welded to a gusset plate as shown in figure. All steel is 836 with Fy is equals to 250 MPa. The electrode used is E60 with allowable shearing stress of 124 MPa. The properties of the member is L 75 by 60 by 6. Given area is 774 mm squared, and the x bar is 23. So that's the location of the force P. Weld size is equals to 6 mm. Allowable shearing stress on gross area is 0.6 Fy. So that's code provisions. So that's a code provision. Provision. Okay. What is the value of load P based on gross area yielding? Okay. So what's the force P so that the gross area or this area will break? Okay. What's the load P? So you can calculate it here. So P is equals to force gross. I mean not force. It's stress allowable force, which is Ft. Ft times the area of gross. So Ft is equals to 0.6 Fy. This is given here in the code provision. Pero pag hindi given, you should know that for stress T allowable is 0.6 of Fy. Okay, so 0.6 times 250 is equals to 150 MPa. So the area gross is also given, which is 774 mm squared. 774 mm squared. So substitute to solve for the force P is equals to 150 MPa, which is in Newton mm squared, multiplied by 774 mm squared. So you can have P in newtons, but in the choices you need kilonewtons. You need to divide this all over by 1000. So you have 116.1 kilonewton. So that's the answer. That's the letter D. Okay. So second question is, what is the value of L1 and what is the value of L2? So when we look at here, what should be the value? This is L1, no? And this is L2. Okay. So first we need to solve for the total length of the weld needed. Okay. So this is number 2, and this can also solve number 3. Okay. So first we know P is equal to stress times the area. The P here is 116.1, and the stress here is considered weld stress, weld shearing stress, which is 124 MPa. Okay, we need to times 10 to the power 3, so you have Newton, and the FVW, that's shear stress in weld. Okay, FVW is equals to 124 MPa. Okay, so the area of weld is given by the provision of 0.707 times the thickness of the weld. This is constant, no? Constant. And wait. Or to solve for the length, no? To solve for the length of the area weld is you need to maximize the thickness. No? So to maximize the thickness, the max thickness of weld max is equals to the member thickness. So the member thickness is given by 6 mm. No? 6. Okay. So this is 6 mm. So we can say that area of the weld is equal to 0.707 times the thickness of the weld, which is 6, times the length of the weld. Okay. So basically, if you have considered a thickness, maximum thickness, you can rewrite the area of weld into this formula. So this is also a code provision. Okay. So you have P, you have shearing stress of the weld, and then you have the area of the weld. Okay, substituting. So you have 116.1 times 10 to the power 3. That's in Newton, is equals to stress of the weld 124 Newton over mm squared, times the area of the weld is 0.707 times 6 times the length of the weld. So solving simultaneously, you have the length of the weld is equals to, so the length is 220.72 mm. Okay, so how can you solve? This is the total length of required total length of the plate, so that it will hold uh, the force P of 116 kilonewtons. So basically, the total weld, length of weld is equals to length 1 plus length 2. Okay, so going back here to the figure, okay, so we write here length total is equals to 220.72 mm. Okay, so how can you solve the required L1 and L2? So basically, you need to balance. So this weld here will hold a force of P2, that's P2, and then the length of weld here will hold the force of P1, P1, okay, P1, and then the line of action of the total P is here. So to prevent failure, we should distribute equally the total length of the weld from here L1 and L2. So basically, you need to generate zero moment here, zero moment. Okay, so you need to, okay, so we need to summation of moment here in the line of action of P equals 0, this is P. Let's assume counterclockwise is positive. Okay, 0 is equals to length 1, say length 1 times x bar. The x bar is 25. It is given here, that's x bar. Okay, here it's 23 pala, 23. It's not 25. Let's change the thickness so that you can see properly. Okay, so basically you can have L1 times 23 minus, no, no, the L1 should be minus because we assume counterclockwise positive. L2 is equals to 75 minus 23. So this is 75 minus 23. That's 52. So this is 52. Okay, 52. And then you transpose L1 to 23 plus, not plus, equals to L2 times 52. Okay. Same idea, no? Some textbooks will apply Varignon's theorem here, but to understand properly the sign convention, I used moment. Okay, and then we just replace P with the length of weld because that is directly proportional. The length of weld is directly proportional to P. Okay, so that's it. Okay, so solving to solve for L1 is equals to L2 times 52 over 23. So that's equal. So that's L1 is equals to 2.2608 L2. So we all know the length total. Length total is equals to L1 plus L2. So you have 220.72 equals to L1 plus L2. So substituting the value of L1 here, 220.72 is equals to 2.2608 L2 plus L2. So solving L2 is equals to L2 is equals to 67.7, 67.68 to be exact. No? So solving for L1 is equals to this 2.2608 times L2 67 times 0.68. L1 is equals to 153.03 mm. That's in mm. Okay. That's the value of L1 and L2. So basically means to distribute properly of the length total of 223.72 to catch the load of P, no? You need the length of L2 should be 67.68 here, and you need the length of L1 that should be 153.03. Okay, so that's the minimum requirement. Okay, 67.68 and 153. So the length one is letter C. and the value of L2 is approximately 68. Okay, so that's how you solve welded connection. Uh, welded connection. Okay, that's all. Thank you.